On my watch, we still have 10 minutes.
Yeah, it's about what I got to, but I want to make sure we don't start ahead of when they've got YouTube running.
Poetically.
West Mansion was a more interesting building, but it was not very good office space. And it certainly wasn't good for this. Yeah, you're right.
Plenty of land to build something.
Yeah, true. Now there are only about a half a dozen of us work here that still remember the place. Christine, are we ready? All right. Welcome, everyone, to tonight's Cosmic Exploration Series. Whether you're joining us in person and survived the thunderstorm here in Houston, or whether you're joining us virtually, I thank you for coming on behalf of my boss, Lisa Gaddis, who's the director here, but is traveling and cannot be here in person, although I believe she's online. I want to welcome you to the final event of this school year in our Cosmic Exploration Series. We are still cogitating on what we might do next school year. I do not have that announcement to make for you yet. We'll announce it when we know, and I suspect many of you are on our mailing list, and that way you'll find out when we know. Tonight, our speaker is David Kring, one of our own here at LPI. David got his PhD from Harvard University, taught for many years at the University of Arizona, and he's been with us for, I'm going to say, approximately 15 years, give or take a couple. I don't know the exact number, but he's been here a long time, and we're grateful to have him. He is an expert in lunar geology and in impact processes. He is currently doing a lot of things to help NASA get ready for the Artemis program missions, the landings on the moon that we hope will happen within the next 2 or 3 years. And tonight we're privileged to have him talk on what might Artemis astronauts encounter at the lunar South Pole. David, thank you.
Well, thank you, Walter, for the introduction, and I want to thank everybody for their interest in lunar exploration and for braving the weather. Yeah, that's quite a storm that rolled through. I sometimes speak downtown at the Houston Museum of Natural Science, and I was giving a talk about impact events, and just coincidentally, every time I said the word impacts, there's a roll of thunder. Now, you know, with spacecraft, we don't like loud noises, so let's hope those are gone for the evening. Okay, so I have to get out of this, I think, and find my presentation. I don't want to stop sharing this. Christine, how do I do this? Oh.
Very short presentation, right?
Hey, it's hovering. That's not a good sign. There we go. Okay. So yes, so let me jump to the first slide here. So I want to say something about Artemis. Some of you may not know what Artemis is. You being in this, probably not very many of you, but the Artemis program involves a series of spacecraft launches that are going to initially go to the lunar South Pole, going to help us explore the lunar surface. Ideally, that will be globally. And this is the first stage in a Moon to Mars program. Now, a critical component of that is this microphone going in and out? Okay, I'll do that. So a critical component of this system is the Orion crew vehicle. And what sometimes people lose track of is there's already been 4 successful Orion missions. And so here they are. There was a pad abort test in 2010. There was the exploration flight test in 2014, an ascent abort test in 2019, and we had Artemis 1 last December. And you can see that there's a series, the capability of the underlying SLS, Space Launch System vehicle, will grow, and that will allow us to expand our footprint, if you will, on the lunar surface. I want to say something about Artemis 1. It's just a wonderful success. We're already thinking about Artemis 2 and Artemis 3, but we have to applaud the success of Artemis 1. This is a little NASA illustration of the flight path of the vehicle. And just to remind you, launch was November 16th, just a few months ago. On the 21st, it approached the Moon. On the 28th, it was at its greatest distance from Earth, about 270,000 miles. And then on December 5th, it was getting ready to do a powered flyby of the Moon that would swing it back towards the Earth. And on December 11th, we had a successful splashdown. And so that was a necessary uncrewed test that gave everybody a lot of confidence in the vehicle. And so that now puts us in line for Artemis 2, which will be a crewed mission. NASA recently announced just next door at Ellington Field who the crew of that mission will be. And so this is kind of exciting. I mean, these are our neighbors, right? So we're going to have 4 of our neighbors going to the Moon for the first time in a very long time. I used to say the year, and it was just too nauseatingly long. So it just isn't the past. It's been a while. And so this is going to be a very exciting mission. There are going to be some proximity ops. That is, they're going to undock and do some maneuvering with 2 vehicles, which will be kind of exciting. They're not going to pass very close to the lunar surface. So I want to throw that out there now for those of you who are anticipating a close approach to the lunar surface. That's just not going to happen. The idea here is to test the human transportation system and crew vehicle. So they're going to be, I think, 10,000 kilometers above the lunar surface, so fairly far away. But that will allow some interesting full disk views from the vehicle. Okay, and then that takes us to Artemis 3, and that's really what I want to be speaking about this evening. The Artemis 3 mission will be our 7th landing on the lunar surface, and that's scheduled for 2025. So next year, 2024, we'll have Artemis 2. The following year, we'll have Artemis 3. So as you can imagine, there are a lot of people working around here at a frenzied but safe pace. And so I'm not going to go through the flight path here of the vehicle for Artemis 3 so that I can focus a little more on what might be encountered on the lunar surface. Okay, but before I do that, I just want to remind you that this is part of a system that is a series of launches, and NASA has recently selected a second human landing system vehicle. So there are 2 human landers, are going to be human-rated landers. The first for Artemis 3 and Artemis 4 is being built by SpaceX, and then Artemis 5 is going to be built by Blue Origin. Each of those crewed missions, Artemis 3 and Artemis 5, will be preceded by an uncrewed demo of those landers. As you can see, these are not Apollo's LEM. These are quite different vehicles, and I'll come back to that point a little bit later in the presentation. So where are they going? They're going to the South Pole of the moon. The South Pole is a strategic outpost on the edge of the largest, oldest basin on the moon. It's called the South Pole Aitken Basin because it stretches from the South Pole to a little tiny crater called Aitken. And it's roughly 2,400 kilometers deep, in diameter. It is slightly elliptical, so that's an average. In this particular diagram, we have colored the elevation so that the red and white colors represent highlands, mountainous type of terrains, and you can see that the South Pole Aitken Basin, which is in a big impact crater, is in fact the lowest part of this region. And in fact, the lowest point on the lunar surface is in a crater that is within this particular impact basin. Okay, so this is a map that actually illustrates specifically the Artemis exploration zone, which is in the South Polar region and has been defined initially to extend from the South Pole to about 84 degrees south latitude. Okay, and so that's the region that you see here. So this is an area that's roughly 360 kilometers in diameter. And since we're in Texas, I just want to point out that that's roughly the distance between Houston and Dallas. NASA has identified 13 candidate landing regions in this area for Artemis 3. All of the white and red triangles that you see on that diagram, we've actually studied. So we've been very busy looking at these potential landing sites and looking at potential traverses that the astronauts could be doing in all of those sites. And of course, we publish that. That's in the public domain, and the deciders, if you will, on the NASA can use that information or ignore that information if they so desire. But I guess the point is a tremendous amount of effort has gone into understanding the lunar surface in this part of the moon and examined it in excruciating detail. And I'll show you a couple of slides later in the presentation where these are such high fidelity studies that we've already identified rocks we would like the astronauts to collect. So that's pretty good, I think. All right, so in doing so, this is a new region of the moon. We've not been there before, and so there are a lot of unnamed features. And in the spirit of increasing diversity and inclusion in our lunar exploration efforts, we've actually had an opportunity to put new names on some of these geographic features. And so 3 names that those of us here at the LPI were involved in is a name for the crater now called Henson. Matthew Henson was with Commander Perry, the first explorers in recorded history to reach the North Pole. Ursula Marvin, she was one of my advisors when I was a student at Harvard. She was one of the original Apollo 11 sample analysts. She is a co-author of what we call the Lunar Magma Ocean Hypothesis. She was the first woman on United States Antarctic meteorite searching expeditions. And I could go on and on and on, just a stellar career. And then Dr. Anna Stoss, she was one of the first women geologists to work in the United States. She mapped a large portion of the Appalachian Mountains. And so she's also recognized with a crater. And I just think it's going to be wonderful. The astronauts get to walk around in the vicinity of craters for these esteemed individuals. Okay, so the first thing you have to understand about the South Pole is the topography is dramatic. I don't want to spend a few slides on this. It's just almost mind-boggling. Here is a rendering that some of our students here have produced. Shackleton Crater is near the South Pole, and I'll illustrate that in a little bit later. There are 3 large craters on on the near side, just beyond Shackleton Crater there, called Hallworth, Shoemaker, and Faustini. And then there is this incredible mountain. Leibniz Beta Massif is the informal name. It also has recently been renamed Mons Mutten for one of the Apollo ladies that worked for NASA many years ago. Hopefully, this, I have to say, we've artificially illuminated this terrain to accentuate the topography because you can see it. As I'll show in a moment, it's a heavily shadowed terrain. And so if you just look at a picture in shadowed, it's hard to appreciate this topography. Leibniz Beta is the tallest mountain on the moon. And it dwarfs Mount Everest, as I'll illustrate in a moment. And you can see it telescopically from the Earth. It's a part of a ring of mountains that were recognized in the 1950s. Okay, so here are two cross sections that go through that Leibniz Beta mountain and their Shoemaker crater, which I also pointed out. So this is just looking at the topography from the summit of the mountain to the floor of that crater. And that's, of course, on the left side. And then I want to draw your attention to the right side. So on Earth, we're very proud of Mount Everest. And it's kind of dwarfed. Okay, so this is fascinating, interesting, dramatic. I mean, you can go on and on with the adjectives, but it's also an exploration challenge. Okay, we have to keep this in mind when we talk about moving an astronaut from one point to another throughout this region. There may be some topographic barriers. Okay, so this is a map that was made here at the LPI that was done by Julie Stopar and one of her postdocs. And by the way, we have a whole atlas online for this region. If you are curious, just do a Google search on LPI Lunar South Pole Atlas and you'll get a whole page of these wonderful maps. The lunar South Pole is right on the rim of Shackleton Crater. So hopefully you can see the circles and the crosshair. So that crosshair is actually right on the rim of Shackleton Crater. One of the things I want to point out in this slide is Shackleton Crater is a simple bowl-shaped crater. Okay, so that's the name we give it, a simple crater, because it is that simple bowl-shaped. Other craters are larger that have central peaks or peak rings, but this is a very simple crater. And so it's much like Meteor Crater, which we use to train astronauts. Okay, so this is an oblique view. It's, you know, for 50 years, we've been looking at pictures from orbit of the lunar surface. And now I want to try to take you down to the surface, get you some feel of what the surface will be like. And so this is an oblique view that one of my former students helped create. And this is Shackleton Crater, and this is a ridge that the Shackleton Crater cross-cut and partially excavated. That SP label is the South Pole. And you can see that that crater is, I've not mentioned this yet, but it's about 21 kilometers in diameter. And I'll come back to that issue in a moment. This ridge is informally called Connecting Ridge, and it is one of those 13 candidate landing regions for the Artemis 3 crew. Okay, so there might be a rocket sitting there. You know, the SpaceX Starship might be sitting right there on that ridge, and two of our astronauts will get out of that vehicle and explore this ridge. And I'm going to, through the evening, I'm going to focus on this ridge and the South Pole as examples of what they might actually encounter. But this gives you a kind of almost a surface level view of what they'll see at the lunar surface. Okay, so Shackleton Crater is a crater. Okay, and so this is a cross section of the crater. The South Pole is over there on the left. And what I've not pointed out yet, and you'll see in greater detail in a moment, is the floor of Shackleton Crater is shadowed. And I'll explain why it's shadowed in a moment. And so we can see the upper crater walls and the rims of the crater, but we can't see easily, I should maybe say, the floor of the crater. And that's true throughout the region. We have developed a technique that allows us to see into darkness on the lunar surface, but it's only in some sites. We now have an instrument on a Korean spacecraft at the moment that is enhancing our views of some of these shadow terrains But this is another operational challenge. We have sites that are permanently shadowed and therefore difficult to operate in. Okay, so I want to show you a little computer simulation of how Shackleton formed. If you've not seen an asteroid hitting a planetary surface, I haven't. I did see Comet Shoemaker Levy 9 hit the atmosphere of Jupiter, but fortunately for us, this is not a common occurrence, at least in the time span of human lifetimes. Of course, geologists go into the field, we analyze the rocks at impact craters, and we can deduce the processes that produce those craters, but we also will use computers with a very advanced physics to simulate that impact event. And so we've done that for Shackleton crater. There's the asteroid just before it hits the lunar surface. And there you go, and watch that clock. So, you know, that's 100 seconds. Things happen pretty quickly. They would happen faster on the Earth. And so the crater is excavated, and now we have our 21 kilometer diameter crater. This is actually a fairly fresh looking crater on the lunar surface. It has not been heavily deformed. And we estimate the age of this to be about 3.4 billion years old. Now, you can see from these computer simulations, we're able to estimate the size and the speed of the asteroid that produced that crater. So we believe it was an asteroid about 1.5 kilometers in diameter, hitting at a speed of about 15 kilometers per second. And importantly, for what the astronauts may or may not be able to sample, this impact event distributed debris around the South Pole. Okay, so if they land at the South Pole or anywhere within about 20 kilometers of this crater, they are going to be landing on and basically sampling debris ejected from this particular impact event. Okay. All right, so as I said, it's a simple crater, and it's like Meteor Crater in northern Arizona, where we use to train astronauts. And I absolutely encourage you, if you've not been to Meteor Crater and you're interested in these things, make sure that you go to Meteor Crater. It's the type of site that you can fold into a trip to the Grand Canyon, the Petrified Forest, Sedona. It's in that area. Okay, so this is a simple crater. As I've said a couple of times, this is a crater that has long been used to train astronauts. So Gene Shoemaker trained astronauts during Apollo at Meteor Crater, and we continue to do so today. All right. So, but there's an important point. There's an important difference. Meteor Crater is the best preserved and I think the most dramatic impact crater on the Earth, but it's puny compared to Shackleton Crater. So there is a little circle Meteor Crater is about 1.2 kilometers across, and Shackleton is 21 kilometers across. And so you can see the relative scale. I have to say, it's a little bit arduous to be hiking around Meteor Crater and in and out of Meteor Crater. And in fact, that's one of the lessons I like to teach the astronauts when we take them there. They need to have an intuitive sense of what it is like to climb in and out of these craters and hopefully make smart decisions as to when to and when not to walk into craters on the lunar surface. Okay, now I've said something about the diameter, but sometimes numbers don't mean something to people, right? What's 1 and what's 21? Okay, so I've put the highway system of Houston on here. Okay, so by the way, you're sitting at the LPI, which is down here by the NASA Johnson Space Center. You know this, we're southeast of the Beltway 8 and southeast of 610. So if you've ever driven around 610, how many have driven around 610? Oh yeah, painful, isn't it? Okay, so now you have kind of a sense of the scale of Shackleton Crater, if you were to drive around Shackleton Crater. Okay, so that gives you a better sense, hopefully, of the diameter of the crater. I've not said anything about the depth. Okay, so I mentioned the Grand Canyon. Okay, the Grand Canyon in cross-section is at the bottom. And to scale is a cross-section of Shackleton Crater above it. Okay, so it's about 4.1, 4.2 kilometers deep. Okay, now I hike down in and out of the Grand Canyon, and it'll take me 4.5, maybe 6 hours, depending on weather. You're not going to do that type of, you're not hiking down to the bottom of Shackleton in a spacesuit, okay, or hiking out. Or if you do go in, you probably won't get out. So scale, as I said before, topography is really dramatic. And one of the things I've said before in other public lectures, you know, if this was on Earth, this would be a national park. It'd be a World Heritage Site. It is just an extraordinary, topographically complex area. Okay, so now I need to say something about the lighting conditions because this is very important. It's in fact one of the reasons that we are going to the lunar South Pole. For those of you who are old enough to remember Apollo, you know there's 14 days of daylight and 14 days of darkness. Okay, that's the equatorial region. The sun rises in the east and it sets in the west, just like on the Earth, just on a different time scale. At the poles, this is the land where the sun never sets. Okay, so the sun is just circumnavigating the pole. It's just going around, okay, all the way around 360 degrees. So the sun is always there except when it dips behind mountains or the uplifted crater rims, okay? So the sun is not very far off the horizon, and so the topography that I've been describing is actually a barrier. It casts long shadows, okay? Now, let's pretend this little crater here is Shackleton Crater. You see the sun circumnavigating, and the upper crater walls, the shadows are always changing, but you see there's a little red circle in the middle. The sun never illuminates that. That is one of these permanently shadowed regions, and those are very, very cold. Okay, so here is a compilation of images captured by the Lunar Reconnaissance Orbiter, which is still in orbit around the moon, and it illustrates this lighting and shadowing effect in this topographically complex region. There are many areas where the deep shadows are permanent, and in stark contrast, if you have the eyes for it, there are summits that never go into shadow. Okay, and so those are areas where you have solar illumination most of the time. I said never, that's too strong. 85 or 86% of the time you have sunlight. Okay, so with regard to the shadows, those are very cold temperatures. There's a little thermometer. Freezing point of water is at the top. Temperatures get very, very close to absolute zero Kelvin. So temperatures have been measured very close to 20 degrees Kelvin, or 20 Kelvin, I shouldn't say degrees Kelvin, okay? And so if there are any volatiles on the lunar surface, they actually might be trapped there as an ice. An ice like water would be incredibly valuable, okay? Water can be used as a crew consumable, that is water. You can separate out oxygen and use that to breathe. Water is a very effective radiation shield. And also you can divide the hydrogen and oxygen for rocket propellant. And so this is a potential resource. And so I've mentioned, without really pointing to it, two resources: solar energy and potentially water ice. Okay, and so that's really what's driven the agency to look at the lunar South Pole. Okay. So let's imagine the astronauts launch from Earth and that their destination is, in fact, the lunar South Pole. So here we are, zooming in on the South Pole. You can see that cratered surface, and I'm just going to be quiet for a moment so you can appreciate. Okay, now let's imagine we're going to continue this flight and kind of zoom in on the South Polar region, on the rim of Shackleton, or that ridge that abuts Shackleton. Don't know if the view out the window of the Starship, the HLS, will be that grand, but man, I'd like to be on the other side of that window. Yeah, okay. So what might be involved once the astronauts have landed? Okay, so let's look into that with the rest of this presentation. So here's a little breakdown of Artemis 3. There's going to be 4 astronauts. There's going to be 2 in orbit, 2 that go to the surface. And I should say that we hope that this system will evolve very quickly so we get 4 astronauts to the surface routinely. But then the first missions will just have 2 going to the surface. They will spend 6.5 days on the surface. It's hoped that they will have at least 2 EVAs. That's kind of the threshold plan, and hopefully 5. Each one of those EVAs is to be at least 4 hours long with a nominal EVA, and I should explain that acronym, EVA. EVA is when they actually leave the spacecraft. So if they go outside the space station, for example, above the Earth's surface, or if they go outside the lander, that's EVA. So each one of those EVAs will be at least 4 hours long, with a nominal EVA duration being 6 plus or minus 2 hours. Now, for this Artemis 3 mission, this is going to be a walking EVA. There's no vehicle, there's no rover like 15, 16, and 17. And so they're going to be limited to a distance of about 2 kilometers from that lander. And so this will be very much like an Apollo 12 or Apollo 14 mission. Now, I want to say something about this vehicle. I said I would say something about this vehicle. So this is the SpaceX Artemis 3 human landing system. Wow. It's over 40 meters tall, okay? Now, I don't know of any place where SpaceX has actually stipulated the exact height of this, but they have released enough information so that you can determine that the crew window is about 40 meters above the surface. Okay, and you can see for scale what the Apollo lunar module was like. Okay, so it's a completely different vehicle. And so we have, with some students' help, been asking the question, well, you know, what does that do for us? Utilize that. And so one of the things we said, well, from 40 meters off the surface, what can you see? And so this is what we call IVA. What can they do from within the vehicle? Okay, and so on the left, that's where we want to start you first. That's a 2-kilometer radial circle. Okay, so that would be the extent of their EVA. Okay, and so we'll want them to look out the window and look at the immediate landscape. And we will have an EVA plan. You know, it will be a line on a map. We want you to do this, that, and the others. Stop here, collect the rock, make a scoop of soil, and so on and so forth. But, you know, it would be smart for them to look out the window and examine the terrain with that plan in mind. Okay, maybe we need to make an adjustment. Now, you see the colored areas? That's actually what they can see. The gray area they can't see from the vehicle because of the topography. Okay, so they're not going to be able to see the entire exploration area, and that's kind of important to know when you're planning a mission. You want to kind of know what it is they can see, and maybe you want your first EVA to be in that area so that you really know what you're getting into while you're evaluating this particular terrain. Now, on the right side is a zoomed out view, so you can see that they've landed on this ridge next to Shackleton Crater. So now you can see all of Shackleton Crater. And again, the colored regions are the regions that they would be able to see from that 40-meter height above the surface at this landing site, which is on the connecting ridge, which is one of the 13 candidate landing sites. So this is kind of an interesting result. And it's the type of result that you can apply this calculation to any of the landing sites, any of the landing regions. And so hopefully this will be, you know, one of the input parameters into any type of final landing site selection. Now I showed you that movie where the shadows are just like rotating like crazy, okay? And this scares some people. It's like, oh man, you're on the surface and you turn around and suddenly you're in sunlight, or you take 2 steps and suddenly you're in shadow. Okay, well that was a sped up movie. Okay, I can't remember the full amount of time. It may have been a year. It's been long enough since the movie was made. I don't remember. But here's a chart that actually shows you what would happen during an EVA. So here are 2 actual pictures of this region, and I'll show you 2 things. One, focus on the yellow circle. That's looking at the shadow line in a crater. And I can't see any difference. And so there's not a significant movement of that shadow there. But if you do look at the boulder, which is in the white circle, that boulder is casting a shadow. And we've measured how that shadow has rotated. It's moved 8 degrees between the time these two pictures were taken. And these were taken in lunar time, 33 minutes apart. And that's equivalent to about 15 hours. Okay, well, an EVA that's, 4 hours, 6 hours, 8 hours long, this little 8 degree, and it would be less than that, is not significant. That is not going to bother anybody walking on the lunar surface. So that's I think, a bit of a relief for a lot of people. Okay, so I've already pointed out that the Artemis 3 astronauts will have these EVAs, and they'll be lasting on the order of 4 hours and hopefully a little bit longer. Okay. So I want to give you some of the options that they might have. And so I'm going to zoom back in to the lunar surface here in the South Pole and Connecting Ridge region. And I want to emphasize this point. We do not know where they're landing. Okay, this is purely for illustrative purposes. I have nothing to do with the landing site selection process. So don't read anything into what I am saying. This is just a candidate region, and I'm using it for purposes of illustration. Okay, so let's now zoom in on the South Pole. There it is on the crosshairs. Now what I've done here is I've overlaid a map of little small areas of shadow. So all the areas now are black here, or kind of a transparent black. Those are permanently shadowed areas. They're always going to be shadowed. So they're cold, and they could be trapping volatiles, for example, water ice that we could use as a resource, okay? So there may be many small PSRs within this region. And some people are worried about going into these. It's like, these shadow regions are very cold. Maybe the physics is completely different and our astronauts will disappear. Well, we've looked at that in 2 ways. So first of all, it's important to remember that both the Apollo 16 and 17 crews went into small permanently shadowed regions. Okay, and right here is Apollo 16 example, where they went into, it's a small one, albeit a small one, but they reported no physical differences in the regolith. They actually got down on their knees, scooped out the soil, picked up a rock. Everything was fine. We've also been looking for, I want to say 5 or 6 years, at boulders that have been displaced in this region and looking at their tracks. And we have seen boulders roll from sunlight into shadowed regions, and there is absolutely no difference in their sinkage rate across that boundary. So we don't think there is a big threat, but nonetheless, you can be sure that they will test those regions with some care when they reach them. Okay, here's a map of the same region, and you see all these colored pixels on it. Those are points in the area that calculations indicate water would be stable if it's there, okay? And this is a function of depth that goes from zero, from the surface to a depth of 2.5 meters. So anything that has a little colored pixel, you could reach with a trench. Okay, sometimes the water ice might be at the surface, but if it's at depth 2.5 meters, you can either core or trench down to that depth. And so one of the things the astronauts will probably be doing in here is trenching and potentially drilling. They already on the manifest are tools to trench. Not yet on the manifest is a drill. So for sure, they have the capability to trench with Artemis 3. It's still unclear whether they'll have the capability to drill. So they can test these models of volatile presence, which I think would be very interesting. If volatiles are where these models suggest they should be, then you can use that result to calculate the amount of water throughout the entire region, and that would be very useful. I suspect the first few trenches, there's not going to be any water there. And so then the exploration plan will have to be evolved to explore different types of deposits. But we'll see what happens. That's the nature of exploration. Okay, so if you go along that rim, a Shackleton crater, there are small craters and there are boulders. And some of those boulders are big enough they cast shadows, which themselves can be small permanently shadowed regions, which we love acronyms in this business, so we call them PSRs. Lots of acronyms, okay? Oh, I'll tell you, as a geologist, when we saw this picture, it's like, oh, your eyes light up. This is a rock exposed. Look at that scale bar. That is over 100 meters in size. Okay, that's big. That's like a highway road cut. Okay, geologists, when the highway system went in North America in the 1950s, geologists remapped North American geology, and there's just a tremendous amount of geology to be had here. Nothing like this occurred in an Apollo landing site. Okay, and so the science that can come out of studying a boulder like this is just, or a rock exposure like this is just extraordinary. And so the geologists are, their mouths are watering. Okay, so our colleagues across the street, so to speak, at Johnson Space Center have been developing a tool set. And basically the tools that were designed for Apollo were right. And so they've been modernizing them, if you will. But, there's going to be collection packs. There's going to be rakes and drive tubes and tongs for picking up. Hopefully they'll be able to be a little bit more, the word's escaping me. Mobile, I guess, is one way in the spacesuits. We hope the spacesuits will be a little bit better than Apollo, but they'll have a hammer and so on and so forth, and be able to collect samples. And now, this is an example of what lunar samples look like, right? Okay, this is a picture of actual samples. These are Apollo 11 samples, as I recall, and I have given public lectures, and somebody in the audience, if I don't address this in the talk, which is what it's now in the talk, I get this question. You're going all the way moon to collect some gray rocks? Yeah. Those are beautiful. Those are beautiful rocks. Okay. Now, one of the secrets to this business is, looks can be deceiving. Okay. So scientists like me, and there's several other scientists in the room like me too, get to peer inside these rocks and use them to explore lunar history and, in fact, solar system history. And here is what they look like when you do that. Okay, is that not beautiful? It's like stained glass. Okay, so what we do is we will take one of those rocks, we'll slice it, and then we will polish it so thin, so it's about 30 microns thick. And then we put it on a microscope. And the colors and the shapes of the minerals there, that's information, that's data that we can use. We can look at that. We can determine the composition of the rock. We can determine where it crystallized, how it crystallized, what happened down at 30 kilometers beneath the surface, whether it erupted on the surface. And so this is just an absolutely wonderful way to study those gray rocks. And by the way, decorate your walls. Okay, here's another one. So I have the sample numbers hidden there way over on the side. And so this is an Apollo 17 sample. This is a basalt, and this is a titanium-rich basalt. This is the type of rock that we actually might mine at some point in time for titanium. And here's an impact melt breccia. We are going to see a lot of these in the South Pole collection, just a lot of them, because it's an impact crater terrain. But it's not just a box of gray rocks. Okay, all right, so, and this is important too. When you tune into NOVA or Discovery Channel shows about the moon, and you get really excited, or you hear the commentator and the narrator really excited about the discoveries that have been made, those all come from samples. Okay, so here's a list of the big ideas generated by the Apollo sample turn. We have the origin of the Earth-Moon system. That is the giant impact hypothesis. Right away with Apollo 11, it was recognized that the moon was once surrounded by an ocean of magma. Then there was all these rocks that seemed to be affected by impact events about 4 billion years. We call that the lunar cataclysm hypothesis. Interestingly enough, that seems to coincide with the earliest evidence of life on Earth. And so there's the impact origin of life hypothesis that postulates that these impact events, when they occurred on the Earth, because everything that occurred on the moon was occurring on the Earth, actually generated the original habitats for microbial life on our planet. More recently, it's been recognized that this very large South Pole Aitken, or SPA, impact event on the lunar far side may have actually generated a period or epoch of magmatism on the near side. And in fact, that the rocks that the Apollo astronauts collected were a byproduct of that far side impact event. And as our analytical capabilities have improved, we've now been able to analyze the small amount of water that exists within lunar rocks. Okay, and so from all of that, we've been able to put together a model, a primitive model, if you will, of the evolution of the moon. And here it is. Okay, now that's kind of the science story behind our lunar exploration effort, but there is what we call an exploration side to this, and that is we have begun to appreciate that there may be more water on the moon than was appreciated 50 years ago, and that water can be harvested, as I already said, for crew consumables, radiation shielding, and propellant. Now, I want to show you something else about the uniqueness of the South Pole terrain compared to Apollo, okay? And so I have here a timeline from 4.5 billion years ago to 3 billion years ago, okay? And, there was a few scientific names on there for what geologists call those epochs on the moon, but you can ignore those. Just pay attention to the billions of years ago. Okay, so here are the ages of the volcanic surfaces that 4 of the Apollo missions landed on, okay? And you can see that they stretch from, about 3.2 to about 3.6, 3.7 billion years ago. That's Apollo 11, 12, 15, and 17. And then we had 2 missions that were in slightly older modified impact crater terrains. They were affected by the Imbrium impact event. That's the Apollo 14 and Apollo 16 missions. And so that basically is the ages, that represents the ages of the terrains that the astronauts during Apollo explored. This is the age of the Artemis exploration zone. It's older by a lot. And so we're going to get a glimpse at a completely different epoch of lunar history, which is interesting for a lot of reasons, which I'll step through a few of them. I should say that the oldest ages within this area, at least of the landscape, the surface is going to be bounded by that South Pole Aiken impact event, because it basically created the mountains throughout the Artemis exploration zone, and it buried the terrain with ejecta from that big South Pole Aiken basin. And the ejecta from such a large basin is going to be many kilometers thick, okay? So the basic age of the terrain that they're going to be exploring is going to stretch from the age of the South Pole Aiken basin to basically the oldest age that represented by the terrains of the Apollo 14 and 16 landing sites. In addition, it's likely within that old terrain that they're going to be sampling even older fragments of rock, some of the impact breccias from an even older epoch of the moon, right back to the very moments when rock first crystallized on the moon. And so we'll get a better glimpse of the primordial lunar crust in this region than we did with the Apollo missions. And I want to now put this in the context or compare it to what we have on the Earth. So this zone, by and large, represents and is going to provide astronauts samples of rocks that are older than any rock on the planet Earth. These rocks predate the earliest isotopic evidence of life on Earth, and in fact, will give us a better assessment of those early Earth conditions, because again, basically what happened on the moon was happening on the Earth. And so we'll be able, within the Artemis exploration zone, to take a very close look at the first billion years of solar system. history. And I always like to think about it in terms of what the astronaut's going to encounter. And so here is a little description. With each step, Artemis astronauts will be kicking up dust that was accumulated for over 4 billion years, stretching back to a period on Earth for which no rock record exists. Artemis astronauts will be picking up rocks older than Earth's continents, and if they are lucky, they'll discover the oldest vestiges of our own planet Earth on the moon, okay? So over there in the upper left corner is a little diagram, and that diagram's there to remind you that 4 billion years ago, 4.5 billion years ago, the moon was much closer to the Earth than it is today. So today, the moon is about 21 Earth radii from the Earth, and at that time, it was about 4, okay? And so in that period of bombardment, there was a lot of debris going from the Earth to the moon and from the moon to the Earth. And so we're going to have our eyes peeled for Earth's oldest rocks in the rocks recovered from the Artemis exploration zone. Okay, I want to close with a little thought here, and this is for the young people in the audience. I don't see a lot, but you know, I've been talking about capabilities and opportunities that the adults have, and so for the students who might be looking forward, I want to point out that there's a lot of ways that you can be involved, okay? You might decide you want to be a scientist like me, great. You might decide you want to be an engineer that's working on the Orion spacecraft, Space Launch Vehicle, the Human Landing System, and so on and so forth. Maybe you want to study to be involved in rockets and propulsion. Maybe you're interested in space medicine. Maybe you're interested in art and music. There is a place for that in the Artemis exploration program. Maybe you're interested in energy and power stations, manufacturing like 3D printing, architecture. There's going to be a base built within the Artemis exploration zone. There's going to be rovers on the lunar surface and so on and so forth. And so one of the points I want to make is, you know, there are lots of opportunities for diverse interest in this initiative. And so some closing words. And so this actually is really important. So Apollo inspired the nation's children. Those of you who are old enough know that. A few footsteps on the lunar surface revealed to them that anything is possible. A few of those children grew up to be planetary scientists. I mean, I loved it when I watched Neil Armstrong and Buzz Aldrin take those very first steps. But I have to say, I've met a neurosurgeon, I know bankers, I know a plumber, people who were inspired by Apollo, and it didn't really matter what their interest was. Apollo, you know, kind of sent the message, I can do anything I want as long as I, you know, put the effort into it. And I think that is a message that Artemis will also teach. I hope Artemis inspires a new generation of children and does so in an increasingly diverse way. Okay, so before I take questions, I want to show a movie. So let's see if I can get out of this. This is a little video that we made almost a decade ago. It's only about 3 minutes long, but it uses lunar reconnaissance orbiter imagery, flies you over the lunar surface, gets you kind of a ground level view of what the moon is like. There are a couple of places where I have built a mosaic of older imagery adjacent to the newer imagery so that you can see where or how that imagery has changed over time. And I just think it's wonderfully inspirational. So I hope you agree. So let's give this a shot.
So we'll take questions now. We have questions online as well. We've got a lot of people that have been watching online. Please use the microphone to ask your question. We'll take one in the room, and then I've got 5 waiting online already. So who has the first question? Right there. Let's over there. I can reach you more easily, and then we'll get to the gentleman there in the middle of the row.
I got a question. Since the bombardment on the dark side of the moon, was it able to tilt the moon? Because I seen the South Pole is kind of like at a flat, not flat, but it's at the side of the moon.
Yeah, the larger impact events may have changed the orientation of the lunar surface. There are models that indicate that. We have no supporting data for that, but yes, it's possible that some of the largest impact events change the spin axis of the moon. And maybe actually, since it's relevant to the issue of water that I've been talking about, if you change the spin axis, then the pole is in a different place. And that means where it's cold enough to trap water is in a different place. And so it's possible if water was trapped 4.2 billion years ago, that may have been trapped in a different place than water being trapped today.
Thank you. So the first question online, are there plans to set up seismometers on the moon by Artemis crews?
I think most people in the science community is looking forward to having seismometers on the lunar surface. NASA just released, I want to say last week, maybe 2 weeks ago, a call for instrument payloads for Artemis 3. I don't know if anybody has a seismometer that's ready to go that quick, because that's just 2.5 years from now. But if not on Artemis 3, surely in the first 2, 3, 4 missions, seismometers will be deployed. There's also an interest in having a network of seismometers deployed on the lunar surface. That'll take a little bit longer to implement, but yeah, the seismometers are important in that they give us a sense of what the lunar interior is like. They give us a constant monitoring of bombardment as it's occurring today. And so there's just a lot of information that they provide.
I imagine a landing of a Starship vehicle on the moon may excavate a large area. Has there been any thoughts of how much regolith may be ejected and whether or not that area may be interesting to study?
Yeah, there has been not modeling of the Starship HLS per se, but modeling of vehicles of different sizes. And that modeling was led by a gentleman at Kennedy Space Center, who's now also at the University of Central Florida. And it is possible that, well, certainly in the immediate vicinity of the vehicle, the regolith, the surface soil is going to be disturbed. And so that first sample, what we call the contingency sample that the astronauts collect, may be of a disturbed site. There is this question of how far out that disturbance is going to be. That will require detailed modeling of the HLS depending on the vehicle. And it will also be affected by the local topography. But yeah, that's an issue that's being examined.
Thank you. So one online, do you expect the properties of the regolith near the Artemis landing sites to be different from the regolith at the Apollo landing sites?
That's an issue of some debate in the scientific community, and that gets to this issue of whether it's very porous and there's the possibility of spacecraft or people sinking. I would say that to first order, we anticipate this regolith to be most similar to the Apollo 16 regolith, because the Apollo 16 mission landed in a feldspathic highland terrain. And so the rock types and the cratering processes at Apollo 16 best mimic the composition and the processes that affected the South Pole. Now, if there's water ice in that regolith, that would be cause a physical difference. We have actually modeled that, and this is the global we, that is our community, not me, not me and my students. But modeling of that has occurred. And if there's up to 3 weight % water in the regolith, mechanically, it's not very different. Okay, and so they'll be able to dig and trench at about the same rate. Once you get above 3%, it becomes significantly harder. Now, we did have NASA impacted one of these permanently shadowed regions with a vehicle and watched a plume of debris ejected and measured the material spectroscopically that was ejected and determined that there was roughly 5.5 weight % ice in that regolith. So if astronauts were to encounter such a cold and ice-rich area, it might be harder to do some of this mechanical drilling. But I have to say that that impact occurred in one of the largest, deepest, coldest of these PSRs, and there's no chance that an astronaut could get there. The spacesuit that's being designed for them it has a requirement of allowing them to work 2 hours in one of these types of terrains, and to get to that site from the edge might take a day. Yeah.
Okay, now when I was in my 20s during the Apollos, and I remember that they were saying the moon is bone dry. And I hear that we'll have swimming pool up there. So I just wonder how much water is there really?
Great question. So, so geologists, by the way, or biologists for that matter, don't like that analogy, bone dry. Okay, you know, bones have like 60, 70% water in them. Even when you dry them, they still have like 40% water in them. But we all understand that term came from when pioneers were going through the southwestern deserts, and people as well as animals were dying, and their bones would be scattered and they were dry. But anyway, we did not have the analytical capability of detecting very small quantities of water that exist in some Apollo samples. And so geologists would say the water is not detectable. In general, they would not say it's zero, okay? But now we have new analytical techniques. And actually, this is a very important point to make. Sample return missions are incredibly valuable, not only because of the science that you can do with them at that time, okay? If they are curated, which they are wonderfully done next door at the Johnson Space Center, 30, 40, 50, 150 years from now, as ideas change and analytical capabilities get better, you can go back to those samples and learn new things. That's exactly what's happened with the Apollo samples in the last decade. Analytical techniques have allowed us to better analyze water contents and other volatile contents. And so we can measure the oxygen, the hydrogen, the fluorine, the chlorine, and that tells us something about the material that accreted to form the moon, and it's telling us something about the internal magmatic processes and crystallization processes that occurred inside the moon, and the volcanic processes that brought that material to the surface. And some of those volcanic materials actually may be an important source for some of the volatiles in the polar regions. So we did a study of a volcanic vent. It's a huge 400-meter tall volcanic vent, about 500 kilometers from the lunar South Pole. It's the largest indigenous source of volatiles in the South Pole region. And we've calculated how many volatiles were erupted, and those volatiles could have hopped to the South Pole and been frozen in the South Pole region. And that's only possible because of these new analytical techniques. Yeah.
Thank you. We'll do a few more questions. And the one online, are there lava tubes close to the Artemis landing sites that can be explored by astronauts?
The Artemis exploration zone is an impact crater terrain. It's not a volcanic terrain. There are, the likelihood of there being volcanic lava tubes is really, really low. Yeah.
David, can you talk a little bit about the sampling technology so that you can sample within these PSRs, but minimize the damage to that through the suit or the tool itself to preserve these pristine water events or ice events?
Right. So it is of scientific interest to go into these PSRs and sample material that may have volatiles. And we have to say may, you know, until you actually go there, you collect the sample, there's some uncertainty. And, you obviously want to avoid sampling technologies or techniques that heat up that sample and cause those volatiles to be released. That's an issue that curation at JSC is exploring. So I don't want to speak for them. So I don't want to really go down that path any further. But it is going to require, when those types of samples are collected, you may not know if there are volatiles in them or how much volatiles are in them. And so there's already a requirement for Artemis 3 that those samples get double bagged, if you will, so that they're sealed twice so that those volatiles cannot escape from those samples and flood the crew cabin or something like that on the return. Yeah, so that's the one thing that I can say that's publicly out there.
Okay, thank you. So why didn't the Artemis mission consider the North Pole as a landing site?
Okay, so the North Pole theoretically also has, well, I should step it backwards. The North Pole definitely has PSRs. We can see them. They are different sizes of PSRs. They tend to be smaller PSRs, although there's a lot more of them at the North Pole. And potentially volatiles are trapped there as well. But during the Constellation program, which is the preceding lunar exploration program, a focus was made at the South Pole for probably too many reasons for me to go through this evening. And when Artemis was stood up, they basically chose one of the landing sites that Constellation had previously selected in the early 2000s. There is some discussion within the science community now that the South Pole has been selected to avoid the North Pole, okay? So there's always the chance that you'll mess things up at the South Pole. And so there's an interest in leaving the North Pole pristine as we learn more about volatiles in the lunar regolith. And so once armed with better knowledge, then we might go to the North Pole.
Thank you, Dr. Carib. I have a question about how difficult it is to get down into the Shackleton crater. How steep is that slope or the grade down in there?
Yeah, if you're on the rim, you're not going to the bottom unless you fall down. It's a steep 30-degree slope, and it's going to be rubble. Yeah, astronauts, I'm sure, will be smart enough if they land on that rim not to get very close. So there's not going to be any interest in landing on the rim and going to the bottom. And then the bottom itself is shadowed and it's going to be very cold. And so I don't imagine a crew vehicle going to the floor of Shackleton crater. There are mining companies who are interested robotically of landing on the floor of the Shackleton crater, but then robotically they try to recover water ice, and then they have to find a way of getting the water out, right? Yeah.
I'm going to restate a question I received slightly differently. Any plans to go to the far side of the moon?
Oh, okay. So when you're at the South Pole, you have 1 foot on the near side and 1 foot on the far side, right? So when I was showing those pictures, we developed a convention. So we did this, I want to say 15 years ago during the constellation period. Okay, and maybe I need to take a half step back. Geologists and most map makers always put north at the top. It's just, that's the convention, okay? Well, when you're at the South Pole, all directions are north. Okay, so what do you do? So we puzzled over this, not very long, but we puzzled over it. I want to say 2006, 2007, and we decided, let's just, as a matter of convention, put the near side at the top when we orient things. So all of our maps that we publish, the near side is always at the top. And so when I showed you those maps of the South Pole region, the near side, there's the South Pole, everything above that line was the near side. Everything below that line was the far side. Yeah. And the South Polacan Basin is itself on the far side. Yeah.
How do you categorize the age of various terrain on the moon? Is that based on like how long it's remained untouched?
Yeah, so ages of terrains. So great question. Okay, so qualitatively, that was done before Apollo landed. It was recognized as an impact cratered surface, okay? And so the longer a surface has been exposed to asteroids and comets hitting it, the more craters it has, okay? So you can look at the surface, you can say, oh, over here, in this little area, I count 100 craters. In the same size area over here, I see 7, okay? Younger terrain, older terrain, okay? Well, once we had Apollo samples, they landed on some of those. You could calculate the number, count the number of craters, and then we got ages of some of those surfaces, like the basalts, okay? And so that's calibrated, if you will, that crater counting chronology. It's not perfect because there are a few Apollo sites, and so that's a chronology that will get better with every mission we send to the lunar surface. But so the ages of surfaces are determined largely by the density of craters on that surface. Now that's a little bit different than the ages of rocks. Okay, you can, if you land on a lava plain, that lava is going to have a single age, and all the rocks produced from that lava will have that same age. But if you have an impact event, it might mix rocks of all types of different ages. So an impact breccia, at an Apollo 16 site might have a 4.5 billion year old rock, and it might have a 3.8 billion year old rock in the same rock. So when you read about ages, you want to kind of parse it. Is that person talking about the age of the surface, or are they talking about the ages of the rocks? They can be the same, but they can also be different. Yeah.
Hello? Okay. What is the axis of the moon's rotation relative to the sun?
Okay. I'm trying to think of the numbers. The sun is about 1.5 degrees above the horizon at the South Pole. So it's not here. Here we have 23.5 degrees. So it's close to 0 on the moon. Yep.
I think I'm going to ask one last question from online, and then we're going to call it a night. So let's see the next one in order here. So in the Artemis program's later stages, do you believe there will be demonstrations of electrolysis of water than currently planned and demos of refueling in lunar orbit?
Well, surely there's going to be demos of recovery and production of water and processing of water. And I don't want to exclusively say electrolysis. but in general, there's going to be a lot of processes. And I should say that, although I've emphasized water, there are other potential ices in the South Polar region, and there are other ways to generate water on the lunar surface. Okay, you can generate water at an Apollo site, where that Apollo 17 ilmenite-rich breccia came from. You can generate water from that particular rock with the right chemistry. Yes, there will be a lot of interest to process water in a variety of ways. And the second part of the question was?
The second part of the question was?
Something about orbit?
And demonstrations of refueling in lunar orbit.
Oh, refueling. So if in fact water ice is found on the lunar surface and it's in sufficient quantities that it can be processed to produce rocket propellant, then there would be an interest. Now, whether that refueling would occur on the lunar surface or in orbit, I don't know. So now these questions are starting to drift into lunar architecture and engineering. And as a geologist, I have to simply say, I don't know.
And that's an awesome statement for any scientist to say. Thank you so much. Ladies and gentlemen, please join me in thanking Dr. Kring for his presentation tonight. Please go ahead and head into the great room where there should be some refreshments, and Dr. Kring will join you there in a minute to answer more questions and chat with you one-on-one. Thank you so much.